Really, the only announcement I have for the time being is the homework on probability is due. They might have said before it was due on Tuesday. Hopefully I mentioned that I wanted to change that due date. But in any case, probability is due Wednesday with the corresponding quiz due Friday. So homework due Wednesday on probability, which we're going to finish today. And the quiz on counting and probability, all that together, is due on Friday. Additionally, the next workbook assignment, as you can see on top of the screen here, the next workbook assignment, workbook 4, which focuses on just probability, that will be due Friday. So those are three due dates. Homework on Wednesday, a quiz on Friday, workbook on Friday. And that's it as far as this class goes. Additionally, the midterm is next week. Midterm is a week from today. So the way, just very briefly, I'll talk about this in more detail next class period, but the midterm, we will all be taking it in the math tutoring lab in the Sims library. Again, I'll send out an email to specify this. You will go in there and take the test corresponding to your group. So all of you in attendance right now, I'm assuming that you are all group A, I believe, or group, I can't remember which one's which. Whichever group you're in right now, this is when you will be taking the test a week from today. That's when the midterm will be in the library. And I will send out a few emails and just make sure you're all aware of this. So does anyone have any questions before we look at the material moving forward? Yes?
Is there going to be a review for like the midterm, like practice?
That's going to be the next class period. But if you wanted to do anything on your own, so the next class period, I'm going over the practice problems for the midterm, and you can do the practice exam as many or as few times as you want. And if it helps, the midterm, you do have partial credit involved as well. They do give you a sheet of paper to write down partial credit. So it's not just a one and done sort of thing. So normally that makes 1 in 5 students feel a lot better. But again, we'll talk more about the midterm next class period. Does anyone have any other questions? And also, I brought a little bit of show and tell. It's a book, it's a math book from 1899 that I found in my office. Apparently used by, or dated by a guy who used it at Tulane in 1927. I'm curious to see what math books look like. A long time ago. I'll just leave it out there. You can look at it after class. So, pretty old book. Besides for that, let's just go ahead and pick up where we left off with the material on probability. So for probability, last time in class, we were talking about the general way of structuring, the general way in which we structure probability problems, which generally comes down to determining, but we start off with the probability of some event, which is the number of occurrences of that event divided by the total number of occurrences. We did this for every single problem, and it's going to be a fairly characteristic thing as we proceed throughout the section. Now, what this problem pertains to, it considers rolling 2 fair dice. So you're just rolling 2 die, ultimately. And so I'm going to detour right fast. The total number of outcomes for the 2 die, I did put this in the appendix of the course notes, so you don't have to think about all the different situations. So it's basically, if you draw a 3 first and then you draw, or not draw, I'm sorry. If you roll a 3 and then roll a 5, then that's the ordered pair, or the point that corresponds to rolling a 3 on the first die and then rolling a 5 on the second. And so we'll come back and use this similar to how we use the collection of playing cards from before. So we'll come back to this momentarily. So let's scroll back up. So that's the visualization we have in mind, just two die. So as you all maybe know, just a standard dice has the numbers 1 through 6. So the first question is, what is the probability that the sum is 3? And when it says sum, so sum implies addition. We have 2 die. So whatever the 2 die land on, you're just adding those numbers together, and you're seeing what is the probability of that sum coming out to 3. So if anything, we need to determine the number of times in which the sum can come out to 3, and then divide that by the total number of options for rolling the 2 die altogether. This is what we talked about. The number of occurrences of the event and the total number of occurrences without any restrictions whatsoever. So let's go down to our diagram. And we are looking for all of the situations in which the sum of the 2 die come out to be 3. Now, really we have, in total, we have 36 different options. We have 36 different options in total, just a 6x6 table. And we need to figure out which ones of those options add up to be 3. Now you could get a 2 with your first dice and a 1 for your second. That sum comes out to be 3, of course. Are there any other ones? Well, you can roll a 1 first and then a 2 second. That sum could come out to 3. Are there any other ones? Doesn't look like it. So we only found 2 options for which the sum of the 2 die come out to be 3. So we're going to scroll back up. Since we only found 2 that add up to 3. So that will be the numerator. Or, I'm sorry, that should be 2. We just found 2 of them. There we go. We found 2 of them that sum up to 3. And then, so that's the number of times the event occurs. Now we divide that by the total number of occurrences regardless of restriction. So there's no more sum is 3. Now it's just asking, well, how many options do we get from rolling 2 die? And so it's the total number of options. That would be the 36. So the 36, again, where I got that from, there were 36 total ordered pairs in that table below. So there were 36 total options. There were 6, or if you want to think about it in other terms, there were 6 options for the first one, 6 options for the second dice. Multiplication rule, 6 times 6 is 36. And so something I should have mentioned last class, I'm going to mention it here and be consistent with it here. They generally want, the majority of the problems want the final answer as a simplified fraction. So I am going to express the answer, and sometimes they'll want it as a decimal, but sometimes they want it as a simplified fraction. And I want to show an easy way of doing this in your TI calculator in one step. Because you can do this utilizing the convert to fraction command in the calculator. So it might be a little bit easier for this example. You might see that this is 1/18 as a simplified fraction. But if you type in the number, click on math, and then enter it's a fraction, it'll do it for you for any fraction. So that'll automatically simplify any fraction for you, just so you don't have to worry about if you did your math correct or not. So that's under math right there. So if you do that, and I'll do it a few more times in case you missed it, but that'll be the way in which I quickly convert these just to make sure that nothing went awry. And then I'll also go ahead and put the decimal just in case they ask for a decimal. So the decimal 0.0556. So they'll ask for your final answer to be formatted as one of these two, either a simplified fraction or a decimal. So you just choose whichever one they're looking for. Okay, so that's just if the sum is 3. Now, part 2, what is the probability that the sum is greater than 7? Okay, so now instead of them saying that the sum is just one number, now the sum could be a whole bunch of numbers. The sum just has to be greater than 7. Let's see, it could be 8 or 9 or 10 or any of those numbers up to whatever the limits of the die suggest. So greater than 7. Let's remember that as we scroll down to our diagram here. Now the sum of the dice, of the two die, has to be greater than 7. Where's one situation of this? These two. 6 and 2. 6 plus 2 is 8. That's greater than 7. What about another one? 5 and 3. Because 5 plus 3 is 8, and that's greater than 7. 4 and 4. I think you might see the pattern. It goes kind of diagonal to just get all the 8s. So now we have all the 8s. And if you tried to get, for example, if you try to select, say, 6 and 1, that sum is 7, which we will not count because we want numbers greater than 7, strictly greater than, not equal to 7, just strictly greater than. So we have all the ones that are 8. Are there any that equal 9 as a sum? And we have 6 and 3. 6 plus 3 is 9, which is greater than 7. We have 5 and 4. We have 4 and 5. And we have 3 and 6. Okay, what about 10? Yeah, we have 6 and 4, 5 and 5, 4 and 6. You might kind of see the pattern as it finalizes here. 6 and 5, 5 and 6, 6 and 6. So it's this lower right triangle. Because of how the diagram here is organized, these diagonals are going to be the same sum. So any diagonal will give you the same sum. And so all we have to do is count all the things that we selected. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And that's it. There's 15 totals for which the sum of the die are greater than 7. We counted 15 of them. And this is how the diagram helped us do that. So we counted 15. We're going to scroll back up with our 15. So the probability of this event happening, the number of occurrences of the event divided by the total number of options. There's 15 different ways in which the sum can be greater than 7. We divide that by the total number of options. That's still the 36. There's still 36 different options for the die, similar to how there was 52 options for selecting one playing card. And the question is, does that fraction simplify? If you missed it before, I'll do it again. 15 divided by 36. I believe that 3 is going to go into both of them. But we click on math and then press enter. And that's it. They give us the simplified fraction. 5 divided by 12. So they might ask for the simplified fraction, which you would give them 5 over 12. Or they may ask for the decimal. And we can go ahead and give that to some approximation of decimal places. And so you would be inputting one of those two answers based off of if they want a simplified fraction or a decimal, rounded to some pre-requested number of decimal places. Does anyone have any questions so far? If not, then problem 3, what's the probability that the sum is either a 2 or a 5? Notice now they're throwing in a little bit of the set theory stuff. They're using or, basically a union, in other words. So the sum either is a 2 or it's a 5. So let's go down to our diagram and find all the situations in which we have a 2, the sum being a 2, or the sum being a 5. So how many of these exhibit a sum of 2? Well, there's only one way in which you can get a sum of 2. If you add up any of the combinations here, you will get something that's not 2. So they said either a 2 or a 5. All right, we got the one that's 2. What about a sum that comes out to be 5? We have, you can roll a 4 and then a 1, and that sum is 5. Or you can roll a 3 and a 2, or a 2 and a 3, or a 1 and a 4. So the first one was sum is 2. The next one, or the next 4, comes out where the sum is 5. And so the or means we select both of them. So we're just counting. How many of these did we get in total? Easily count that to be 5. 1, 2, 3, 4, 5. So we have 5. That's the number for the particular occurrence. So it comes out to be 5. Let's scroll back up. So the probability of that event, we have that the numerator is, we counted 5 for that occurrence, and we divide that by the total number of possible dice rolls that we have. 36 still. Now it turns out this is already simplified. You'll find that out pretty quickly if you try to convert it in the calculator. It'll just spit out the same number. So it's already simplified. If they ask for the decimal, go ahead and give it to 4 decimal places. And so one of these two will be your final answer for that problem. This is how to deal with probability that involve rolling 2 die. Now, does anyone have any questions about any of these before we move on to example 8? If not, let's go ahead and move on. Okay, so an experiment consists of drawing 1 card. So that's the visualization. You're drawing 1 card from just a standard 52 card deck. You're saying let E be the event that the card drawn is a king. Okay, so now we're visualizing drawing a king, perhaps. And then they say find P of E with an apostrophe. Okay, let's break down what this means. They're giving us notation here. So they're giving us notation. So if we use their notation that they gave us, we did this for the Venn diagram problem as well. The probability of what they want us to find, which is that notation, that is still the number of occurrences of the notation that they gave us. Again, we did this for the Venn diagram, divided by the total number of options. This means that we need to interpret what does E with an apostrophe mean. Now, E, just by itself, the card drawn is a king. So off to the side, let's figure out in words what E apostrophe means, because they tell us explicitly that E represents drawing a king. Does anyone remember what the apostrophe represents?
Everything except for that thing.
Everything except for that thing. So what does E apostrophe mean in this situation?
Every card but the king.
Every card but the king. So in other words, not a king. That's what E not means, or E complement. We call it a complement, of course. So it's the complement of drawing a king, which is not drawing a king. So what we're trying to figure out is how many options do we have for not drawing a king? Well, how many options do we have? How many kings are there in a deck? Yeah, and if you're not familiar with playing cards, I always have a few people who are not too comfortable with them, so I just want to make sure I emphasize the 4 cards in our diagram in the notes. One resembled as a K, that's the king. As you can see, there's 4 of them. They ask for queens, that there's 4 queens, and a Q for queen, and there's 4 jacks as well. So J for jacks. So in case you didn't know that, it's queen, that's a jack, that's a king, and there's 4 of each. And they're generally called face cards. Sometimes they'll call them face cards because they have faces. So there's 4 kings. So if there's 4 kings in the deck, but we're looking for not kings, well, how many not kings are there? It's going to be 48 in total. This is how the complement helps us out a little bit. There's 52 cards in total. If 4 of them are kings, then how many are not kings? 48. And that's how we find it. So there are 48 cards, and if you counted all of them, you'd go 1, 2, 3, blah, 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 blah. And you would count 12 for each row. 12, 24, 36, 48. So it's 48 cards that are not kings. So the top one would be 48. And so the denominator would be the total number of options, which would be 52, the total number of cards. And so we either express the answer as a simplified fraction or as a decimal. I'll put both, just in case it's one or the other. Again, the calculator will tell you immediately. And I guess for completion, 3, the number in total is the 52. There we go. Okay. 48 divided by 52. Convert that, it's just 12 over 13. So most of the problems ask for a simplified fraction. So you would, if this one asks for a simplified fraction, you would tell it 12 over 13. As a decimal, 0.9231. I'll pick 4 decimal places. So your final answer will be formatted as one of these 2. Does anyone have any questions about this one? If not, we're visualizing a deck of playing cards yet again, for example, 9. A single card, so still just 1 card is drawn from a 52 card deck. They're telling us that R is a symbol. So R is some symbol that represents a red card, okay? F is a face card. For face card, I mentioned before, it's every card with a, human face. There's, how many were there? 4, 8, 12? There's 12 in total. So we're going to find the probability of, that's interesting, R complement union F. So they gave us exactly the notation. They want us to find the probability of R complement union F, which if we were to completely rewrite this as a fraction, what are the number of options for this weird symbolism that they have now given us? And how many options do we have in total? Well, let's try to break this one down. So let's try to figure out what that symbolism means. R complement union F. Let's try to break that down into words so we can translate what we are looking for exactly. Now, if R is a red card, then R with the apostrophe, or R complement, is going to mean it's just the black cards. Because remember, the apostrophe means not, which means it's not a red card. We don't really have other options. It's not a red card, which means it's a black card. So we can break this down a little bit. So it's a black card. The union symbol means or. So I'm going to put or. So that's what, should I use a different color for that? Union symbol is going right here. The R complement goes right here. And then the F is a face card. It's a black card or a face card. So now we know what we are looking for. We're choosing every single option that is either black or a face card. The or means that we choose either one. If that was an and, the upside down union symbol, which is the intersection, we would choose the overlap between the two. But it says or it gives a union, which means we select either or. So now that we have the visualization in mind, now we need to figure out the number of options for these. Now that we know in words what we are looking for. So we're looking for a black card or a face card. So let's scroll down to our diagram. Well, the total number of black cards is 26 in total. In fact, it says there's 13 clubs and 13 spades. 13 plus 13 is 26. So we have 26 black cards. And it also says or face cards. It's every card with a face. So that would be these three that I'm highlighting in red. These are all the cards that have faces. How many cards are there in total? 3, 6, 9, 12. There's 12 face cards.
We were looking for the overlap. Would it be those top 6?
It would be the top 6. So if it used the wording, well, if it used the upside down union symbol, which would mean an intersection, which means and, we would be looking for those 6 face cards that are in both sections. So that answer would have been 6 for the numerator. But we don't have the luxury of doing that. And hopefully you all may remember that the answer is not simply 26 plus 12. We fell for this last time because we would be counting stuff twice. It is true that there's 26 black cards and there's 12 face cards, but in total, there's not 38 because you would be counting some twice. Instead, you have to subtract off how many they have in common, or just simply count using the diagram. So there's 26 black cards, 12 face cards, but you subtract off the 6 that they have in common, because those 6 you're counting twice on accident. And so that's 26 plus 6, so 32. My math right? Okay, cool. That's 32. Or if you counted all of them, you would count 13, 26, 27, 28, 29, 30, 31, 32. You would figure it out either way. So we counted 32 cards that are either black or face cards. So there's 32 options for that. And then the total number of options we have, it's still 52. You can still pick from any one of the 52. We're drawing one card, which means we're drawing one card from an option of 52 choices. So if you can figure that part out, so notice if you can figure that part out, everything else follows really easily. These problems for this whole chapter focus more so on the logical aspect rather than the continuation of the problem and this sequential series of steps like we did in the previous chapter on financial math. So 32 divided by 52, we can figure out what that looks like as a simplified fraction. (32 divided by 52). Oops. Figure that out as a simplified fraction. There we go. 8 over 13 would be the simplified fraction, or if they ask for the decimal, 0.6154. So whichever one they ask for. Okay. Does anyone have any questions? Okay, so let's move on to example 10. There's 8 thank you notes, and there's 8 envelopes. Accidentally, the notes are randomly inserted into various envelopes and mailed without checking the addresses. So you have these 8 thank you notes that you write to, I guess, 8 different people. There's these 8 envelopes already written out, all the addresses, but carelessly you just kind of put them in randomly and don't even think about it. So they could, you might send the wrong thank you note to somebody else. So that's the visualization if you need one. What is the probability that you actually accidentally put them all into the right envelopes? That's what we're trying to figure out here. What's the probability of that if you accidentally just put all of the thank you notes into random envelopes? What are the chances of that actually being correct for all of them? You would imagine it's probably not a very high probability, and that's what we're going to figure out. What are the odds of that? So they don't give us any symbolism, so I always default to using the E. So let's go ahead and start considering. We'll start off with, what is E? What does E represent here in words? Does anyone have any idea?
Is it possible thank you notes in the envelopes?
Well, remember, it always follows the word probability. What is the probability that they will be inserted into the correct envelopes? Correct envelopes. I'm going to highlight that because that wording may seem familiar. I use that for a different problem that we dealt with earlier on in this section. The problem with the wheels. So how many correct ways are there to put all of the envelopes, write all of the thank you notes into the correct envelopes. What's that?
Is it 64?
Don't want to overthink this one. How many ways can you do it correctly? One way. It's just like that problem with the wheels on the bike lock, and it was how many correct, however I worded it back then, how many correct combinations were there for the bike lock? There's just one. How many correct passcodes are there for your phone lock? There's only one. This is the same idea. That's why I wanted to emphasize correct envelopes. So the number of ways in which you get the correct delivery of the thank you notes to the envelopes is one way. So again, that's one that students generally tend to overthink. That would be one way. So if anything, the numerator is just going to be one. Now, what's the denominator going to be? So the denominator is the total number of options. So now there's no more correct envelope. Now there's just how many combinations can you possibly have? And the answer is not going to be just 8 or 64. Does anyone have any intuition how we would proceed with this?
Like, so each person has like one envelope that will be correct for them. So it'd be like 1, 8, then 1, 8 on the bottom. And so you do it 8 times.
You're dancing around the right approach. So you're correct. So the reason why I haven't been doing dashes for the previous problems is because we've only been dealing with drawing or rolling one thing or one set of things. You draw one card. So inadvertently, we're doing one dash. We're looking at a set of rolled die, so that's one thing we look at. Here we are dealing with 8 envelopes. So now we're going to deal with 1, 2, 3, 4. I guess let me write this below. We're dealing with 8 dashes though, ultimately. 1, 2, 3, 4, 6, 7, 8. 8 dashes for 8 envelopes. Now we ask ourselves, how many options do we have for each envelope? So you take the first envelope in your hand. You have all of these thank you notes spread out on the table. How many can you choose from? All 8. So you grab one of the thank you notes, one of the 8 thank you notes, and you put that into the envelope. All right, and then you put that one away. All right, you toss that one. You grab the next envelope. Now, how many thank you notes do you have to choose from? Well, it's not 8 because you just got rid of one of the thank you notes. You pick up from one of the 7. And I think you might see the pattern from here. 6, 5, 4, 3, 2, and 1. Or if you're familiar with the wording, this is 8 factorial. And if you don't know what that means, that's okay. It's 8 with the little exclamation point. You've seen that in high school. So what does that number come out to be? I don't know, probably pretty large. Factorials grow very, very large. In fact, I wonder if I could just find it here. Oh, there it is. So that's 8 times 7 times 6. I just don't feel like typing it out in the calculator. You'll get the same answer. 40,320. So again, if you do 8 times 7 times blah, blah, blah in the calculator, you'll get the same thing as I have here. So as a ratio, you have a 1 out of 40,320 chance of doing that correctly. It's very, very small odds that do that correctly. I anticipate though, so the fraction's already simplified because the 1's in the numerator. You can throw it in your calculator and you'll get the same fraction back, which will further emphasize this. I anticipate though with this problem, they're going to ask you to provide the decimal. So notice, depending on which calculator you have, they're either going to give you the whole answer sprawled out, or they're going to give you scientific notation. So let's write this below a little bit. 2.48015 573 e to the negative 5. This is what came out of my calculator. Exactly this. The negative 5 just means you move the decimal place back 5 places. So 1, 2, wait, I'm sorry, 4. Wow, I'm messing up today. Move it forward 5 times. There we go. 1, 2, 3, 4, 5. And what does that come out to be? 0, 0, 0, 0, 0, 0, 2, 4, 8. There's a good chance they'll break it up to 5 or 6 decimal places. But what it's trying to say is that there are incredibly small odds. There's a 0.00248% chance of that happening, which is very small percent chance. So they could ask for this answer, which I wouldn't imagine they would. They would probably ask for the decimal. And if you get this weird display in the calculator, then this is how you proceed. Another thing that may help, if it says negative 5, expect 4 zeros in front. So we added 1, 2, 3, 4 zeros. If it said negative 6, expect 5 zeros, and so on and so forth. Does anyone have any questions about this envelope problem? If not, we're going to look at example 11. So what example 11 says, there's a family with 5 children. Well, in a family with 5 children, you're avoiding twins and triplets and all that stuff. What is the probability of having 4 boys and 1 girl in any order? Well, if anything, they didn't give me any symbols, so I'm going to start off with the same thing, default to E. Now, what's interesting about this problem that we haven't dealt with before is that there's a bit of dependency among the different positions that we have. So we haven't had really this dependency before where we are considering multiple inclusions. So for example, we've only included just kings or just black cards, and maybe we've sometimes looked at 13 hearts, for example. So we haven't really considering 2 numerical options simultaneously. So instead of just what's the probability of 4 boys, that also includes 1 girl. And so if we try to generalize this to dashes, it's not going to work out very easily. So, and another reason to justify this, so if you tried to do the dashes for this problem, how many options would you have for the first one? If you're trying to get 4 boys and 1 girl, well, it also depends on when you have the girl. If you have her first, then the rest of them have to be boys, and then you have 1 option. But if you have the girl second, so that's where it starts to get a little ambiguous. Or in other words, this is kind of an addition rule in disguise. That's what it comes down to. So let's instead think about all the options. We're just going to count them, just physically count them. So let's just think about the circumstances that can happen. And this is for the number of, I suppose, the number of the event happening. So you can have a girl for your first child. I'm going to denote that with a G. The rest of them have to be boys, automatically. In order to have the 4 boys, 1 girl restriction that is set. Or maybe you have a boy first, and then you have a girl. Then the rest have to be boys. Or maybe the first 2 children are boys, and then you have a girl. And the next 2 have to be boys. Remember, this is all under the requirement that we have 4 boys and 1 girl. That's why for any row that I draw, there should only be 1 letter G, because there should only be 1 girl in our restriction. And if you see you might see the pattern already. Maybe you have a girl first, or I mean 4th rather. And the last one would have to be a boy. How many more options would I have from here? Just 1 more. You could have a boy as your first 4 children, and then a girl last. And the addition rule comes into the fact that there's 1, 2, 3, 4, 5. So there's 5 options for that. So again, this is where it switches, it kind of quickly switches to an addition rule. A little tricky problem. And this addition is caused by the restriction considering 2 or more things simultaneously. So now the question is, what do we divide it by? What are the total number of options we consider? Which I'll try to put that down here. So the restriction made us use the addition rule, but if we don't have a restriction anymore, we don't have to use the addition rule. We're going to go back to the multiplication rule, because now we're considering just in general, how many combinations of children can you have? So you're still having 5 children, 2, 3, 4, 5. And how many choices do you have for each child? 2. You have a boy or a girl for either. The restriction is gone. That's 2, 4, 8, 16, 32. So it's 5 over 32. So we can either have 5 over 32. 5 over 32 ends up being the simplified fraction. You just typed it in your calculator, you would just get the same number back. I'll go ahead and just type in the decimal. 15625. I'm pretty sure this one asks for the simplified fraction, but here's both options just in case. The 2's are just the number of choices of child you can have, either a boy or a girl for each child. So 2 options for each. And you can have boys again and again, so you can repeat. So that's where the 2's come from. Are there any other questions before we look at example 12? If not, example 12 says there's an experiment that consists of tossing 6 coins. One of the 6 coins has a head on both sides. So you have 6 coins, but one of the coins, it's tampered with, or there's a heads on both sides. Compute the probability of obtaining exactly 3 heads. Or in other words, containing 3 heads and 3 tails as a consequence. And the reason I emphasize that is because example 12, the restriction acts the same way as the previous problem, as example 11. So that means we are going back to determine the number of options we have. What we need to do is figure out the total number of options by counting for the situations in which we get exactly 3 heads. Now, one thing works in our favor. Since one of the coins has a head on both sides, we automatically get one of the coins for free. So instead of computing the probability of exactly 3 heads, since one of the coins is automatic because it's got a heads on both sides, really we're just looking for the probability of 2 heads. Since one of the coins is always going to be heads no matter what, then we have that one locked up. So now, really what we're doing is we're looking at 5 fair coins and considering how many options do we have to get 2 heads out of 5 fair coins. So to figure this out, we need to figure out the number of options we have. So that fixed coin brings us down 1 number, which is good because that's 1 less dash. That's 1 less multiplier in our combinations. So we're going to have to figure out all of these options. There's 5 coins, 2, 3, 4, 5. 2 of them have to be heads. The first 2 can be heads, and then the next 3 can be tails. Or the third one could be heads. So this is a lot of conditional stuff. If the first one is heads, then how many options do we have? So the first one could be heads, and then the last one could be heads. And the point is practically the point is you want to write out as many of these until you see a pattern. Now, if anything, I see 4 for whenever heads is the first coin flipped. These are all the options in order for us to get exactly 2 heads from this. But what about if heads is, say, so let's say you flipped a tails first and then a heads. Tails first and then a heads. Now you could have heads, then 2 tails, or tails and heads and tails, then tails and tails and heads. So the second column are the total number of options for if you flip a heads twice. Now, the first column gave us 4 options. The next column gave us 3 options. What do you think the following column is going to give us? 2 options. So the point is, it's a very gratuitous process, and there is a formula for this that is not the most fun, which means we have to do it this way. So it's 5, and then we get 4, and then the next one is going to be 3 whenever you have a heads third. Or actually 4 and 3. I don't know why I wrote a 4 and 5. Just 4, then 3, and then 2. And then there's 1 more. So the 4 is corresponding when a heads is flipped first, then the 3 is when a heads is flipped second, and then what happens? And then the next one is when a heads is flipped third, and then what happens? And the final one is when a head is flipped fourth, and then what happens? So again, it's not practical to write out all, well, 4 plus 3 plus 2 plus 1, 7, 8, 9, 10. It's not practical to write out all 10 options, but you want to see the pattern fairly quickly. So that tells us the total, the options for that specific event. Now, I am curious about something. Okay, so there is a formula to it. It's not a very fun formula. It's something called combinatorics. You don't ever have to know what that means, but if you are interested in that, then you need a little formula for that. But in any case, that's the number of options we have counted. And so now we need to figure out what are the total number, which means the restriction's gone, so we don't have to use the addition rule anymore. Because now it's just, well, one of the coins is fixed, so I'm just ignoring that and dropping it down to 5 coins. Just like in the previous problem, there's 5 coins. And how many options do we have for each coin? Heads or tails, heads or tails, heads or tails, heads or tails, and yet again, heads or tails. Or the 5 coins that are not fixed. I know the problem says 6 fair coins, and we just got rid of one of them because one of them gave a heads for free. So this is just 32. From here, we can go ahead and simplify 10 over 32. I'll just go ahead and fill that in as 5 over 16 right fast. And then we can figure out whatever the decimal version is. I'd imagine it would ask for a fraction, a simplified fraction, but just in case. 0.3125. Does anyone have any questions about this one? Example 13, this is, I believe, the only example. There might be 1 or 2. It'll ask you to find the odds for and against. And this is its own formula. We haven't seen anything about odds for and against in this section. So I believe this is the only problem that uses it. So I'm not focusing on it too much. So what they're doing is they're telling us the probability, and really the 2 formulas the odds for is just, you take the probability and you divide it by 1 minus that probability. There's also odds against. Which is just flip odds for. And by flip, I mean flip the fraction. And we'll see that here. So just flip odds for. So if odds for is a fraction, you just flip it. Or take its reciprocal, in other words. So those are the 2 formulas, and right below, I'm going to just write out what it is for A. Because here it's assuming that 1/5 is the probability. They're giving us the probabilities. So what it's saying is, if we look at odds for part A, that's 1/5 divided by 1 minus 1/5. That is by plugging in 1/5 for every single situation of the probability. And figure that out. You could put this in the calculator, or you could split it up one bit at a time. Really what I would do . 1 divided by 5, in parentheses, because that's the numerator, divided by more parentheses for the denominator part, 1 minus 1/5. I use parentheses for the numerator, I use them for the denominator, and they will want your final answer as a fraction. So hopefully you remember this command, convert to fraction. 1/4. And that would be your answer for the odds for parts of part A. So it'll ask you odds for, and then it will ask you for odds against for each part. So odds against is you take odds for, whatever you got in the previous part, and you just flip it. So instead of 1/4, like we got in the previous part, it's going to become 4/1. It's going to become 4/1. And you might think, well, let me reduce that down to 4. This problem does not want you to simplify that far. It wants you to keep your final answer as a fraction. It's a kind of a ratio reason why. 4 out of 1, instead of just saying 4 and not having a denominator to complement it. It's really a context thing, kind of a nitpick in my opinion, but they want you to keep this answer as a fraction. So I am intentionally not simplifying that 4/1 to just 4. Again, just that's a my math lab thing. Personally, I wouldn't care, but let's move on to odds, odds for and against for part B. As part B, they give 0.56. So odds for, this one actually might be easier because decimals generally seem to be more well received. I'm plugging in the 0.56 they gave us into the formula for odds for. And simply, it's simply calculator work from there. .56, that's the numerator. Divide that by the denominator in parentheses, 1 minus 0.56. So we get 0.27 repeated. They want the final answer as a fraction. 14/11. That's a lot nicer number. That would answer the odds for. Then odds against. Which means the 14/11, we just simply flip it. So instead of 14/11, just 11/14. That's it. That's all you have to do for that one. Does anyone have any questions about this? If not, this is the part of class where I'm going to go over any homework problems from probability. If anyone has any requests, happy to do those. If not, I'll just keep doing them until we run out of time. So I'll assume that you can figure out the first few on your own. So how did everyone feel about the cards problems? Should I go through some of the ones that I might not have covered, or? Well, so how about this one? Maybe you all try this one. What's that?
I was about to forget one. It did have one. I can't remember the number one.
Well, you figure that one out. You all try this one out right fast. Just try to think about this one. Probability of drawing the 2 of diamonds. Well, how many ways do you have? How many options do you have for drawing the 2 of diamonds? Yeah, so don't overthink that one. You just have one. You just have one. There's only 1 2 of diamonds. That's a specific card. So there's only 1 2 of diamonds. So your numerator would automatically be 1, because remember we do that n of e over n of s thing. So it'd be 1 divided by the 52, because you're drawing 1 card. So they want a simplified fraction, just 1 over 52. Did you figure out the number?
Yeah.
So hopefully that was pretty straightforward. So what was the one before that? I'm drawing a black card. How many?
1 over 2.
Yeah, so 26 options for the black card. In fact, I might have done this one in class already. Can't remember. Black card, there's 26 of them. So then you would replace the 1 with the 26, because that's how many options there are. That actually does simplify, though, to just 1 over 2. Because they want a simplified fraction for this.
That was question 9.
Question 9? Okay, let's look at question 9. All right. Remember me doing this one in class? Should A be rejected? Well, the 2 things we talked about for this one was you reject them if the sum is greater than 1 or if any of the probabilities are negative. Here, if you, for A, it's referring to this top row. If you add all those together, I mean, just look at those numbers. Do you think you're going to get 1 or something greater than 1? It definitely looks greater than. So, well, should it be rejected? That would be yes. You should reject it, which means it's not going to work. Well, simply because the sum's not 1. And then the next one, should B be rejected? B down here be rejected? Definitely should be, because there's a negative probability. You should never have a negative probability. Negative probability is right here. So you should reject it. because one of the probabilities is negative. And then the last one, I'm guessing the last one's good, by process of elimination. We did that one in class. Let's look at maybe another one of these boy-girl problems. So in a family with 6 children, what's the probability of having 6 girls? This is one of those counting problems, one of those addition rule problems. This is one of the ones in which we had to count. So how many options do we have for 6 girls? If we think about these specific situations, well, what's one option in which we can have 6 girls? You might think, let me just write. Okay, what's another option? Well, if we're stuck on the restriction of having 6 girls, which means I have to write 6 G's. There's only one way. This one, so this is probably the one you hope you get in your homework. There's only one way. As opposed to the total number of combinations in which you can have 6 kids, 3, 4, 5, 6. So 6 kids, and you have 2 choices for each one: boy, girl, boy, girl, boy, girl. That's why I'm putting 2s for all of these. And that should be 64. So it's 1 out of 64. One out of 64. I like this question, so let's do this question. I really like this question. What's the probability of choosing, so ignore all that wording on the top, it just explains what cards are, of choosing a black ace of diamonds? No, it's 0. There's no black ace of diamonds. Yeah, I made the same mistake when I first saw it. So if you're not familiar with the deck of cards, they're asking for a black ace of diamonds, but diamonds are red cards. Diamonds are red cards, but they're asking for a black diamond ultimately. There's no black diamonds. You can look all around here. There's no black diamonds. There's only red ones.
That's kind of wrong.
Yes, that's also kind of why I like the problem. So it's 0 divided by, well, it doesn't matter. It's just 0. There's no chance of getting a black ace of diamonds. It is very wrong, no doubt, but so I did this problem as well, but I think it was a 4 instead of a 5. So hopefully that will get you started on the right path. And I did 10 in class. So there's the first 10 there. The homework's due Wednesday, so you can also ask me after class. If you have any questions, you can ask me after class on Wednesday. I'll stick around and answer questions. I don't have a class after this one. So if you have any questions, just write down the numbers, and you can ask me then. And I'll be happy to answer any of them. Other than that, sign the roll sheet if you missed it, and have a good day.
Have a nice day.
I have a question though.
Yes,
Do you make problems on MyMathLab?
I do not.
Because they don't, I like to use a question help, but sometimes a lot of times they don't have a question help. That really help me, but.
Yeah, so really for this class,